Okay, yesterday we stopped at example 1.3, which provides you an equation for the surface. However, the surface is in fact an elliptical locus, so it's just a line. However, it does not specify the variation in the z direction. So 2x to the square plus y to the square equals to 6 simply describe an elliptical ellipse on the xy plane. So as the figure suggests, the locus can be extended upward and downward because there is no restriction about the variation in z direction. So it's an ellipsoid standing in parallel with the z-axis. All right, and in the previous slide we have told you that once you have two differential lengths that are tangential to the surface, so as the figure suggests, you have DL1, which is begin from this point, that is 1, 2, 0 on the plot. So DL1 is a tangential vector. Now that's is starting from point 1, 2, 0. And you need another differential length, say DL1, so that you can do the cross product, that is DL1 cross DL2, to find the direction of the normal vector on the surface. However, in this equation, there is no specification about the z direction. Therefore, you have the degree of freedom. You have the degree of freedom to specify the first differential length. That is dl1 equals to dz az. 好，再讲一遍哈。因为这个题目里头，它其实并没有第一个线第一个 dl1 的这个线差分向量，别人可以自由选的，所以你可以看着这个图选出它该有的一个可以有的一个differential length tangential vector 那在这一点上面，其实是有无限多的 tangential vector 因为一个面上面的一个点嘛，事实上有无限多的切分向量可以经过这一个120这一个点但这一个 dl1 等于 dzaz 是一个简单的直觉可以看的。你说老师我没有这个直觉吗？我们慢慢培养这个直觉吧好不好所以在这个题目里头，它的第一个 dl1 其实并不需要从题目给的条件去计算事实上这也是根据题目给的条件去找出来的所以这是 dl1。好，那 dl2 的话，我们就用正规的方法，也就是写出这个 differential length 的一般式，然后把这一个曲线的关系式做一次的微分，就像我们昨天讲的来去找出这个 dl2 OK。 Alright, so to find out the second differential length dl2, you begin with the equation that is 2x to the square plus y to the square equals to 6, taking the differentiation. So that will be 4 times x dx plus 2y dy equals to 0. So we end up with dy equals, not yet. Note that this relationship is dependent of x and y coordinates. So you need to substitute coordinate, that is x equals to 1, y equals to 2. So you have 4dx plus 4dy equals to 0. So what is the significance of this relationship? That is, one portion of dx, one portion of variation, changes in the x direction equals to minus dy. One portion of variation in y direction, not that in the negative direction. So the next step is write up the general expression for the differential lengths in Cartesian coordinate systems. Substitute the known condition we have here. All right, so what kind of substitution? Oh, yeah, over here. Yep. So we have a dx ax minus dx ay. So the second differential length is this one. And the normal vector, as we already know, can be found by taking the cross product of the two tangential vectors. So that's dl1 cross dl2 divided by the magnitude of the cross product. And it ends up as 1 over square root of ax plus ay. So you can verify the calculation yourself. All right, so here is the normal vector, uninormal vector for the normal vector at this point only. If you are checking up at other positions, the calculation should be done accordingly, should be done again, because the tangential vector becomes a different one at other positions. So do take practice about this process yourself with your homework, all right? Okay, next is the concept of differential surface. So we already discussed the concept of differential length, that is a vector, it has a magnitude, but it's supposed to be infinitely small, but it has a direction. Now we have, now we are looking at the definition of differential surface. Again, because it's a differential surface, so the surface area is relatively small, but is that a vector or a scalar? Well, it's a vector, so you need to describe the direction of the surface, which is done by elaborating, describing its normal vector. So we use the normal vector to represent the direction of the surface. So here are three examples. If you have a surface expanding on the xy plane, then its normal vector is pointing to the z direction. Here you have a surface placed along with the xz plane, so it's pointing to the y direction, and here's another direction. And the size of the differential surface is described by what? Described by the dot product of the two vector, by the two vector. So it's simply like a parallel path like this. A parallel plane is expanded by two vectors, as long as the two vectors are not placed in parallel. As long as the angle between the two is not 0 degree, they can expand a small surface area, a parallel pipe area like this one. And the size of this parallel pipe can be described by the dot product. So that will be DL1 dot DL2, and it end up with the with what? Dot product. No, I'm sorry. Not dot product, cross product, all right? 外基啊，对不起我刚才讲错了。两个向量所张出来的面积是由它的外基大小来决定所以 ds 会是 dl1 乘 dl2 乘上 sin alpha 是两个向量的夹角So the size of the parallel pipe can be found by taking the absolute value of the cross product of the two vectors, like this one. And equation 1.29, just taking the absolute value of the cross product. So it only gives you the description about the size, the area size of the parallel pipe. And if you have a full description about the cross product, you can end up with not only the magnitude but also the direction of the surface. So the differential surface ds, which is a vector, if you write in this way, it can be found by taking the cross product of the two tangential, the two differential vector. Note that you have a positive and negative sign. Why? Because a differential surface is not a closed surface. So it has two directions, two normal vectors, pointing upward and downward. So you have both positive and negative sign in its description. So it should be positive and negative DL1 cross DL2. All right? Okay, so if you're taking the cross product of differential lengths along reference directions, you end up with this kind of differential surface, just as what we've seen in the plots of the previous slide. Okay, so dx, dy, dz, ax suggests that the surface is expanding on the yz plane. So its normal vector is pointing toward positive and negative x direction. All right? Okay, the third concept is the differential volume. And this one is a little bit different to the previous two because a differential volume is a scalar. Differential volume is a scalar. Differential length, differential surface are vectors, while differential volume is a scalar. 所以呢，给你一个空间中的一个体积的描述，空间中一块区域的描述，它有方向吗？没有嘛，对不对？它只有大小。那跟前面的线差分、面差分类似。体差分也是由3个线差分向量的运算可以得到So the differential volume can also be derived based on operation of the 3 non-identical differential lengths, and the operation is the so-called scalar triple product. Note that in our first two lectures, we have already introduced the idea of a scalar triple product. That is A dot B cross C. And the differential volume is defined in the format of scalar triple product. So if you have 3 differential lengths, DL1, DL2, and DL3, you can imagine that DL1 cross DL2 expands a differential surface, which is this parallel pipe drawn on the plot. And so here you have the area size. And this is size description. How about AN? AN is the vector, the normal vector produced by the cross product. And now that the second term is formed by taking the dot product of the third vector DL3 with the normal vector expanded by the first two differential lenses. So you can imagine this calculates what? This calculates the height of the parallel pipe. 所以 DL1 跟 DL2 的外基给你这一个立方体嘛，矩形体的底面积大小，而它们的外基也同样描述了 AN， 也就是说这个底的法线方向，而后面的这个运算 DL3 内积 AN 给你什么？给你 DL3 这一个 differential length 在 AN 方向上面的投影量，所以你得到的是这一个被踹了一脚的爱玉的高，所以就像你知道的体积等于面积乘上高度嘛，假如没有被踹一脚的话是类似正方形的，那踹一脚之后就歪掉了嘛，Right, so with the definition of a scalar triple product, we can find out the volume expanded by non-identical differential lenses. All right, and the result, since it's described as a scalar triple product, it's a scalar. So dV is written in this way. Not a vector, it's a scalar. And it can be write as DL1 dot DL2 cross DL3 or DL2 dot DL1 cross DL3 because you are taking the absolute value. Well, the absolute value is critical. Why? Because volume is a positive number. You don't have a negative volume, right? So you only have the positive number. So you need to put absolute value operation on it. So the order doesn't matter. You can, it all give you the same result. The size, the magnitude of the scalar triple product. So the absolute value of the scalar triple product of three vectors originating from a point is the volume of the parallel pipe having the three vector as its contiguous edges, all right? And if the three differential lenses are aligned with x direction, y direction, and z direction, the volume integral can be found by taking the product of the three. However, this description is only valid for Cartesian coordinate system. For cylindrical and spherical coordinate systems, you cannot just take in the differential in the three reference direction and having the volume product. Why? Because the x, the y, and the z are all description with length. 这边会扯到一件事情，就是我们在描述坐标系统的时候，它的描述 x, y, z 其实本身自带长度。我不知道你还记不记得球坐标系统或柱坐标系统，或者是你可能有碰过所谓的极坐标系统 （polar coordinate system）。极坐标系统里头的那个参数是什么 ？r 跟 phi 嘛，对不对 ？r 是有长度的 ，phi 呢 ？phi 是角度，所以 phi 本身不带长度。 所以在柱坐标跟球坐标系统，你会遇到西塔，会遇到 phi 这些东西是不带长度的，所以在算体积的时候，或者在算面积的时候，它会别的坐标系统会有点尴尬哦。但在直角坐标系统里头，它没有这种尴尬哦，因为ds dy dz 本身自带长度啊，所以假如你找出来的这个3个参考方向刚好是 ds dy dz， 因为它们互相正交，所以你的体积简单就可以算成是这3个的相乘啊。OK。And before we leave this section, here are some descriptions, some supplement description about the Cartesian coordinate systems. So equation 1.34 is a general equation for the definition of an arbitrary surfaces. So it just tells you that a surface equation is a function. Involves description in all 3 directions, x, y, and z. And it can be determined as function f of x, y, and z equals to 0. And one example is equation 1.35. Here is not that 1.35 is a kind of a special equation that it describes a planar surface. 平面啊，1.34是通例啦，1.35是一个特例啦。它跟1.35它指的是一个平面，啊，平的平面哦，不是曲面哦。所以，假如这个平面的话，假如它长这个式子的话，那个 x y z 跟 a b c 有什么关系？假如它这样写的话，其实就是那个 a b c 就是那个斜斜的平面切到 x 轴的坐标。y 的坐 b， 那 b 就是它切到 y 的坐标 ，c 就切到它 z 轴上面的那个坐标啊。所以当你一个平面斜着摆的时候，它会切过 x y z 3轴的3轴啊。那切过那个坐标点刚好就是 a b c 3个点啊。所以应该说这一页算是一个补充知识了哈。And equation 1.36 helps you to define what? Well. 1.36 has 2 equations. The 2 equations describe a line, an arbitrary, a line, because 1 equation to give you a surface. 2 equations, the intersection of 2 surfaces is a line, is a curve. So in equation 1.36, you have a function f, which is a description of 1 surface. Function g is the description of another surface. If you can satisfy both equations, you are located on the line intersected by the 2 surfaces. Alright? Now, 所以关系式 f 跟关系式 g 是2个面的任意面啊，平面啊，曲面都可以，任意面的描述。那所谓的一条线，或者说这2个面的交集啊，就会是一条线啊。所以，假如说你要去描述空间中的一个特定的线的话，那你可以把它写成是像这样子的2个面的交集，好不好？好。Alternatively, a curve is specified by a set of 3 parametric equations with an independent parameters. So it's another description that you can use to describe a line. So here we have a description of a surface, a line, and a line. All right? Okay, let's move on to section 1.3. We will discuss about cylindrical coordinate system and spherical coordinate system. As the figure suggests, you are looking at cylinders. Here are 2 cylinders. 2 cylinders. So in cylindrical coordinate system, we presume that the axis of the cylinder is in parallel with the z direction. in Cartesian coordinate system. So we assume the, so what are the three reference direction of Cartesian coordinate system? They are R, phi, z. Well, to be more specific, in textbook, sometimes it writes as RC, phi, z. C suggests that is the R of a cylindrical coordinate system. While in spherical coordinate system, we have R, theta, phi. To be specific, we have RS, theta, phi. So you know that the R direction or R axis is a little bit different for the two coordinate systems because they are actually defined differently. Okay? So in cylindrical coordinate system, the z-axis is simply the z-axis in Cartesian coordinate system. There's no difference. And for a two-dimensional coordinate system, this is referred to as the polar coordinate system. 有印象吗？二维系统里头 ，R 跟 phi 是叫什么？极坐标中文叫极坐标嘛，这个你在学什么？学 complex number 的时候，复数的表示方式嘛，对不对？你可以用它的距离跟它的角度 r 跟 phi 来表示复数空间中的位置嘛，所以对应的是 x 跟 y。所以你还记得吗 ？r 跟 s 的关系 ，r 跟 y 的关系x 等于什么 ？r cosine theta 嘛，cosine phi。y 等于多少 ？r sin phi， 所以事实上，在这边这个就是所谓什么坐标系统的转换，位置 position 在坐标系统的转换。那当然我们等一下还会讲到在驻坐标系统里头的位置的转换，跟直角坐标系统的转换，当然三维空间就稍微再复杂一些 ，OK。Okay. So in cylindrical coordinate system, the three reference directions are labeled as R, phi, and z. Note that z is the same as the one in Cartesian coordinate system. So it has direction, and suppose here is the origin of the cylindrical coordinate system. So you see the z-axis is pointing in this way. All right? So what is in our classroom is defined, you try to imagine that our classroom is defined in terms of a cylindrical coordinate system with z-axis placed here. So where is your z direction? 在你的位置上 z direction, okay, pointing upward, simple, the same as the one we have with Cartesian coordinate system. So we have a uniform. So this is a uniform direction. However, in polar coordinate system, all right. So suppose at this point, what is the r direction at this point? It's pointing this way. Note that the direction in a coordinate system is the arrow is pointing to the direction of the parameters becomes a larger number. So here we have r and phi. So why it's pointing outward? Because r value becomes larger and larger as it gets to this direction. So this is the AR direction. How about phi direction? Phi direction is is defined as the angle between the position, the line from origin to the position with the positive x direction. So this is the phi angle. And phi angle increases as it rotates counterclockwise on the plot. So at this point, what is phi direction? What is its phi direction? It's in this way. Okay? However, if you are looking at a point over here, where is its r direction? Well, it's going to this way, all right? How about the phi direction? It's going to this way. So note that the AR direction are different in the 2 points. And the A phi direction are so different at the 2 points. So if I stand on the z-axis, and where is your r direction is pointing that way, how about your r direction is pointing that way, right? And your phi direction is not the same as the phi direction of his. So uniformity, or in cylindrical coordinate system, the 2 parameter, the 2 reference direction do not hold for the uniform property. So any 2 points in any 2 different points in the cylindrical coordinate system do not have the same r direction and do not have the same phi direction. So that's a difference between cylindrical coordinate system and Cartesian coordinate system. Another thing we can see here is so what is this cylindrical surface stands for? The cylindrical surfaces stands for the surface expanded by a constant r number. So this one has a larger r number, this one has a smaller r number. 所以这边的图的话，你可以想象说，在直角柱坐标系统里头，你有 r 西塔 phi 嘛？不是啦 ，r phi z。所以 z 是一个定值的话，你在空间中看到的是什么样的一个面？水平的平面嘛，假如 z 是定值，假如 r 是定值的话，你会看到的是什么面？就这边看到的圆柱面嘛 ，r 大一点，那个圆柱胖一点嘛 ，r 小一点，圆柱瘦一点。那假如 phi 是一个定值的话，你看到的那个它所张出来的平面是长什么样子？一半的无限大平面，垂直的，因为 phi 是一个定值，那表示什么 ？r 可以是任意的值 ，r 可以对啊 ，z 的变动范围是多少 ？What is the variable range for z direction? Minus infinity to positive infinity, right? Okay. How about the range for r? The minimum value of r is what? 0. What is the largest number? Infinity. So r value varies from 0 to infinity. How about phi? The minimum number for phi is 0. The maximum number for phi is 2 pi, or 360 degrees. So note that phi itself is not a length. It's a degree. Right? It's an angle. Phi is an angle. It's not a length. So phi itself, or the phi itself, describes the difference in degree, not a difference in length. So the phi itself is not a length. So that's also different from Cartesian coordinate system, right? 所以稍微我们这边就理解一下它们之间的差异除了我刚刚提到的 r phi 的方向并不具一致性，然后 R 的变动范围是0到无限大 ，phi 的变动范围是0到2派，也就是0到360度。底 phi 本身是角度的差异，并不是长度的差异，所以我们要在柱坐标系统里头去描述一个长度的时候，只要牵扯到 phi， 就要小心一点，要做一些调整，好不好？好。So, for example, if you have a disk, rotating disk, 像是 if you have a rotating disk, and there are two ends. One is over here, the other is over here. And as the disk rotates, you see that in a specific time interval, the change of angle in the phi direction is the same for the two ends, supposing that they are not moving. How about the velocity? Well, intuitively, the one that the circumference of the disk moves at a higher speed, right? The one in the middle moves slowly, right? No. So, to describe the length traveled by a specific time interval, you need to describe the length moved by the velocity is what? Velocity equals to distance times t. Okay, dt. Okay. Well, so what is suppose the difference in phi is the phi, what is the speed of this one? That will be r1 d phi, and here's r2 d phi. So if you try to describe the length traveled by the two ends, you need to add up the description about the length at with respect to the rotating center, so that you can get a length. 所以底 phi 本身只有角度的差异，并不是长度的差异。所以你要描述强度的差异，在极坐标系统或者在柱坐标系统里头描述长度的差异的话，你就要乘上那一个观测点的位置离圆心离轴不是圆心离轴心越大，那它的速度或者移动的距离就越大，可以吗？后来 So, how about this figure? This figure shows an example of a differential volume expanded by 3 reference directions in Cartesian coordinate system. So the height of this structure is dz, and here's dr. However, the description about the length along the phi direction becomes r d phi, right? As I already stated. So d phi itself is not a length. You need to times the distance between the observation point and the axis to provide the length description along the phi direction. Also note that a very distinctive difference between cylindrical coordinate system and spherical coordinate system is the r is defined differently. R in the spherical coordinate system is the distance from the observation point to the origin. 球坐标这边有提到一个重要的事情现在最好现在就记起来球坐标系统里头的 r 是任意空间中的任意点到球心的距离，那个 r， 但在柱坐标系统里头的 r 不是柱坐标系统里头 r 是你任意点、任意观测点到 z 轴的最短距离。 到 z 轴的距离等于距离，不是到球心哦，是到 z 轴哦。哦，有没有看到他在画的时候，那个 r 都是 P 点的 r 是到这里 ，Q 点的 r 呢也是到这里。哦，不是到这哦，不是哦，不是这样子的哦。哦，所以柱坐标系统跟球坐标系统 r 不太一样，所以一个写作 RC， 一个写作 RS 啦。假如你看古模的话，哦。Alright, so beware about the difference between R definition in cylindrical and in spherical coordinate system. Oh, alright, so if you want to describe the size of that volume, that will be the R times R d phi times the Z. Oh, okay, that's the differential volume in cylindrical coordinate system. Let me write up the differential volume for spherical coordinate system. That becomes dr times r d theta times r sine theta d phi. Oh, so yeah. The differential volume in spherical coordinate system becomes a little bit more complicated. All right? 先预告一下了哈。Okay, so the three orthogonal surfaces defined in the cylindrical coordinate system of a point are a cylindrical surface if you have a constant r, a planar surface, half infinite planar surface if you have a constant phi, and a horizontal planar surface if you have a constant z. Alright? 好，所以注意哦，虽然说第一个圆柱面好理解嘛，哈，但这两个平面要小心，它们还是有点差异的哈。z 等于 constant 其实就是一个水平面嘛，所以它是水平面上无限延伸，但是 phi 等于定值的话呢，其实它是从 z 轴开始往外无限延伸，因为 z 是正负无限大上下延伸 ，r 呢则是从0开始到正无限大，所以虽然说这两个都是 phi 等于 constant 或 z 等于 constant， 虽然都是平面，但是一个是无限大，一个只有一半的无限大，好不好？Alright, so the final notice about another notice about the variable range. The range is r starting from 0 to infinity, phi from 0 to 2 pi, and z goes from minus infinity to infinity for the cylindrical coordinate system. The three orthogonal surfaces define three curves that are mutually perpendicular. So any two of them are straight lines, and the third is a circle. So if you specify two of the three coordinates, you will end up with one line. If r and z are fixed, you will end up with a circle in the space. If r and phi are specified, you will end up with a vertical line by varying z, by varying the z parameter. If phi and z are specified, you will end up with lines pointing outward in space. 好吧，这边一个练习吧，你自己想想看吧假如说 r、phi、z 这三个参数里头，其中两个固定，那你会得到一条线假如只有 r 可以任意变动的话，你得到的是一条从 z 轴射出去的线那假如 phi 只有 phi 能够变动的话，那就是一条圆形的线假如只有 z 可以任意变动的话，那就是一个空间中的一条垂直平行于 z 轴的线 ，OK， 自己想象一下。OK， so So in this slides, in this figure, we will try to describe important property about cylindrical coordinates. There are also important property for coordinate systems. The first thing is, for every position, its reference direction are perpendicular to each other. 所以 for 任意个点上，它的 R 方向、Z 方向、Phi 方向都是怎样互相正交的？你自己再练习一下，看一下 A 点、B 点，它的 R 方向、Z 方向跟 Phi 方向是怎样？第一个，它都往那一个参数越来越大的方向变动，所以 R 方向都是朝外的 ，Z 方向都是朝上的 ，Phi 方向呢就是顺着那一个在 XY 平面上的投影量的逆时针方向旋转。 好不好？看清楚这一点。然后 non-uniform，they are not uniform。所以除了 Z 方向是有一致性以外 ，R 方向跟 Phi 方向在不同的位置就不一样。OK， 好吧，这大概是这一页里头要强调的事情。OK， 那另外我们有提到的是面积体积的描述啦，或者是面积的描述。OK。 So here we take a closer look at this figure. For example, if P point, the coordinates P point of P point is 2, R equals to 2, Phi equals to 10 degree, and Z equals to 5, and Q is located on the 227. 这是我随便乱周的 example 啦，OK。所以你会发现。 R 跟 Phi 都是 R 跟 Z 都是位置啦 ，Phi 是角度，好不好？好，角度。So the coordinates for point P is R, Phi, Z, and for point Q, which is close to P, you can add up the differential difference in terms of R, Phi, and Z. So Q can be described as R plus dr, Phi plus d Phi, Z plus dz. And we can write up the differential lengths, differential surfaces, and differential volume for this description. Before that, let me show you. Okay, the right-handed screw system also abide for Cartesian for cylindrical coordinate system. So if you have IR cross A phi, you end up with AZ. If the cross product is done by A phi cross AR, you ended up with minus AZ, all right? So A phi cross AZ gives you AR. So the same property, the same right-hand screw properties holds for cylindrical coordinate system with the order of R phi Z, okay? And here are the expression for the differential lengths. So what is the difference between this and the differential length in Cartesian coordinate system? In Cartesian coordinate system, dl equals to what? dsx plus dy plus dzaz. Here you have dr ar plus r d phi a phi. Okay? Why? Because d phi itself is a difference in angle, not a length. You need to times r at this position to provide you the length along the phi direction, the length of change along the phi direction. So it's r plus dzaz. OK? 所以主要的差别在这里，因为 phi 方向上面只有角度 ，phi 方向是角度的长度的描述，所以你在牵扯到长度的时候，你要用到 r 底 phi 才能够代表一个长度。同样的问题会被带到 differential surface 跟 differential volume 的描述里头So if you check out the differential surfaces, so here is the surface expanded on the RZ direction, RZ plane. So it becomes dr dz a phi. So can you find the planes for this description? 你看到这个图里头，你还是有个六面体嘛，对不对？只是这个是平的，这个是平的，里面是弧形， 这个外面的也是弧形，哈。所以 1.40B 呢，给你的是哪里？前面、后面，啊，所以它的方向是正的 A phi 跟负的 A phi。这一组呢，这一组描述在哪个面上面？那是对应到这边哪两个面 ？That's plus minus r d phi dz ar. So the normal vector is pointing to positive r direction or negative r direction. So that will be two curvature surfaces on the outside and the inside. Now, because you have some changes in dz and some changes in r d phi, and the normal matter is pointing this way and that way. Okay, the third group is plus minus r dr d phi az. So you know that it's the top surface and bottom surface because the az vectors suggest it's pointing upward or downward. And the region is a sector. Sector expanded by dr and r d phi. Okay? So the differential surfaces are somewhat different than the ones in Cartesian coordinate system. Finally, the differential volume description is dr times r d phi times dz. So you have an r stands in the front for the differential volume description in cylindrical coordinate system. Okay? All right. Whoops. Let's break for 5 minutes, and we will come back with spherical coordinate system. 我要先